Okay, in this video, we're going to do another example of using strong induction to prove a formula for recursive sequence. So here's this example that we're going to do today. So consider the sequence which is recursively defined by a sub 1 is equal to 1, a sub 2 is equal to 2, and the recursive formula this time is that a sub n is equal to a sub n minus 1 plus 2 a sub n minus 2 for n bigger than or equal to 3. So again, we're going to play a little bit first to try to get some, well, first of all, just to make sure you understand what this recursive formula is doing, what it's saying, and then also to try to come up with a guess as to what a closed form formula is for this. All right, so first of all, we know that a sub 1 is given to us as 1. A sub 2 is given to us as 2. We always need these sort of seeds to start the recursive nature here. And now a sub 3, we have the two previous ones, which is why we can play around. So a sub 3 is a sub 2 plus 2 times a sub 1. So that's 2 plus 2 times 1. So that's 4. Okay. Now a sub 4 is equal to a sub 3 again, because you're taking that 4, plugging it into this formula. If n is equal to 4, and n minus 1 is equal to 3, and n minus 2 is equal to 2. So that's like this, a sub 3 plus 2 times a sub 2. Now again, we already have those two guys ready to go. We just got this one just in time. So it's 4 plus 2 times 2, and that gives 8. All right, so maybe we're starting to see a pattern here. A sub 5 then is a sub 4 plus 2 times a sub 3. A sub 4 is 8. We just got that guy. Plus 2 times 4. Well, that's also 8, so we get 16. Now this starts to feel like, man, this must be a pattern, right? So let's just do one more. A sub 6 is a5 plus 2 times a sub 4, which is equal to, well, a5 is 16 plus 2 times 8 is also 16, which is 32. Now you notice these are even numbers here, but actually that wouldn't be the right guess to make as far as how to express them. They're not any old even numbers. They're actually powers of 2. So what we're going to do is prove, plus the first one's not even, it's 1, which is a power of 2. So we're going to prove that a sub n is equal to 2 to the power n minus 1. Okay, and this time I won't do the sketch. I'm going to go right into the proof. So here we go, proof. So we're going to prove that closed formula that although the sequence was originally defined recursively, it turns out there's a closed formula that a sub n is just 2 to the n minus 1, where we don't have to do any recursion. So again, we tell the reader we will proceed by strong induction. So what's the base case? So a sub 1, we again, we have two base cases. We see that that is 2 to the 1 minus 1 because that's 2 to the 0, which is equal to 1. Good. And a sub 2, what we're hoping is 2 to the 2 minus 1, which is 2 to the 1 power, which is 2. And so, yes, we're good. The two base cases that we need to start the recursion work for the closed formula. Great. So now the inductive case. Let me give myself some room here. So, okay, in the inductive case now, we assume we need strong induction. So we assume that for all natural numbers, k less than or equal to n, we're going to assume that a sub k is equal to the closed formula to the k minus 1. And now we will show that if you look at the next one, which is a to the n plus 1, that will be equal to 2 to the n plus 1 minus 1, which is just 2 to the n. Okay. So now, by applying the recursive formula and the inductive hypothesis, we find the following. So I'm going to take a sub n plus 1 by the recursive formula, that's a sub n plus 2 sub times a sub n minus 1. Okay, but both of those fall in the strong inductive hypothesis range, right? They're both less than or equal to n. So I can just use the inductive hypothesis. That's 2 to the n minus 1 plus 2 times 2 to the n minus 2. Okay, but now there's so many powers of 2, and we saw this happen when we played around with specific cases, that we always wind up multiplying by another power of 2. So now we get 2. Now, if I move this 2 inside, I get 2 to the n minus 1 because I add 1 to the power. All right, but now I have 2 of them, right? So now I can say that there's 2 times 2 to the n minus 1. But that's, of course, equal to 2 to the n. And we just want to note at the end that that's the same thing as 2 to the power m plus 1 minus 1. And so we're good. So now, hence, by strong induction, we have found that a sub n is equal to 2 to the n minus 1. Very good. So we'll see, this is another example of strong induction, but this is 2 examples now where we've proven that recursively defined sequences can be equal to some closed formula. And we'll see one more example of this in a different setting.